Hello, in this video we're going to sketch the curve fx equal to x squared over x minus 1 squared. Now if you'll notice, we've been given both the derivative and the second derivative, and we just want to ensure that they're fully factored before we get too far into our question. So we notice here in the numerator we just have a negative 2x, which is definitely factored. The denominator is x minus 1 cubed, definitely factored. Over here we have the same type thing, two linear factors, so everything's factored and we're good to go. We're going to start off by listing the domain of fx. So let's look here for the domain. Any values that might be impossible for the function will come from the denominator, and it looks like x equals 1 would be a value that would give a 0 denominator. So we'll exclude that, but we'll be good with everything else. So we'll get minus infinity to 1, union 1 to infinity. Now we can go ahead and find that x-intercept. It looks like the x-intercept is happening at x equals 0. And the y-intercept looks very similar. If we plug in f of 0, we also get 0. So the x-intercept and the y-intercept is the same. It looks like it's going through the origin. Now we're going to have to calculate the horizontal asymptote. So we want to do the limit as x approaches positive infinity of x squared over x minus 1 all squared. To do that, we apply the quotient theorem to get rid of that pesky minus 1. So we have the limit, x approaches infinity, x squared, x squared. Of course, those will cancel, and so we'll get a limit of 1. We'll do the same technique as x approaches negative infinity of x squared over x minus 1 squared. Using the quotient theorem, again, we'll get rid of that minus 1. So we'll have the limit x approaches negative infinity of x squared over x squared, which again will give us a value of 1. So this tells us we have a horizontal asymptote at y equals 1. Now before we do the vertical asymptotes, we're going to want to draw out our sign diagrams. So we're just going to make a little bit of space here. And we can go ahead and draw the sign diagrams for both f, f prime, and f double prime. So just referencing the functions we have above, for fx we're going to have a 0 at 0, and it's even. Then it's going to be undefined at 1, which is also even. So when we pick a value bigger than the 1, say 10, we get positive, positive, positive. This means that the function is always above the x-axis. For the derivative, we have a 0 at 0, and we have it being undefined at 1. Pick a value bigger than 1, say 10, we're going to get negative. So then we'll have negative, positive, negative. Our function is decreasing, increasing, decreasing. Now it looks like we have a relative max at 1, but because the function is not defined at 1, that doesn't in fact give us a relative max. But we do get a nice little relative min right here at 0. We get ourselves a relative minimum. Now we can look at the second derivative. We're going to have it being undefined at 1, which is an even power. And we're going to have a 0 over at negative 1/2. So we pick a value bigger than 1, say 10, we'll get positive, then positive, and then negative. So we have concave down, concave up, concave up. That means right here we're going to have a little inflection point. Now, going back to the limits, we can use this sign diagram for f to help us determine the vertical asymptotes. So if you notice, we have the function being undefined at 1. So we expect to have a vertical asymptote there. And if we write out the limits, we have the limit x approaching 1 from the left of fx. That will give us, well, it's got to be some type of infinity because we're dividing by 0. And the sign diagram tells us that since we're from the left, we're going to have a positive infinity. Similarly, as we do the limit, x approaching 1 from the right, we're also going to get a positive infinity, because if you look on the right side of 1, we also have positive values. So this gives us that we therefore have a vertical asymptote at x equal to 1. We can also write all of our intervals of increasing, decreasing. The sign diagrams give us that quite nicely. So if we notice, we have increasing on 0 to 1, and it's decreasing minus infinity to 0, union 1 to infinity. For concave up, we have it on minus 1/2 to 1, union 1 to infinity. And concave down, we have it on minus infinity to minus 1/2. Now, we're going to have to calculate a value of the actual function. We would need to calculate f of 0, but that's already been done for us, as that's the origin, or the y-intercept and the x-intercept. We can write that down here just for completeness. And so f of 0 is equal to 0, and we have our relative min there. But we don't know what f of negative 1/2 is, and we're going to need that value so we can figure out where to put the inflection point. So we plug it into the function, and we get the following. Negative 1/2 squared over negative 1/2 minus 1 squared. So in the top, that gives us a quarter. In the bottom, that gives us negative 3/2 squared. If we keep working here, we'll get a quarter divided by squaring the 3/2 will give us 9/4. Those 4's will eventually cancel, and our final answer will be 1/9. So we have all the information we need to graph, so let's go ahead and make some space and sketch the graph. So you want to make a nice big set of axes, label them x and fx. We can go ahead and put down our asymptotes. If you want, you can do it in a different color. Sometimes it makes it look nice. So we have our horizontal asymptote at y equal to 1. And we have our vertical asymptote at x equal to 1. We can go ahead and plot the couple points we have. We have it going right through the origin here at 0, 0. And this is a relative minimum. Just to the left of it, we have an inflection point. So we'll put that here. That's at minus 1/2 and 1/9. So just note I'm graphing it below the horizontal asymptote because 1/9 is less than 1. And we have our inflection point. Now from there, we should be able to graph the function. We know that it's going to be always above the x-axis because it's always positive. It's going to initially come here and it's going to be decreasing. So it's going to be decreasing, decreasing, decreasing. We're going to have it hit that minimum, so kind of round out. Then it's going to approach the asymptote as it increases, and we know it's supposed to go to positive infinity, so it has to be up here. On the other side, we know it has to come from positive infinity, and it's supposed to be concave up, so we'll have a shape that looks roughly like that. So we'll go ahead and do our best to graph it now. Again, we want to start concave down. Then we want to become concave up. Approach that asymptote, and don't forget the arrowheads. Then again, we come from the asymptote, concave up, and approach the horizontal asymptote. Again, if you notice here, it crosses through the horizontal asymptote, and that's totally fine. You can cross horizontal asymptotes, especially as you're taking relatively small values. The horizontal asymptote just deals with the y values as x approaches either positive or negative infinity, and here we're nowhere near infinity. So it's completely fine to cross the asymptote there. Thanks for watching.